So here in the hexagonal, as I said, it's also half of the tetrahedral sides are filled. It's only that the tetrahedra then stacked, the third layer of tetrahedra are stacked in a different way, and therefore it's a hexagonal lattice. Okay, and here simply to show again, you can do everything with the hexagonal what you did with the cubic. You can fill all the octahedral sides. This is the so-called nickel arsenate structure. And you fill half of the tetrahedral sides. This is the wood side structure. But in the so since it's an ABA structure type, the symmetry is lower. As I said, here the nickel is still surrounded by the arsenic in an octahedral way, but the arsenic is surrounded by nickel in a trigonal prismatic way. So the hexagonal structure, in the cubic structure in sodium chloride, the sodium had the chlorine in an octahedral way surrounding the chloride and vice versa. Here it's different, and now people already who work on MOS2 or MOT2 understand now this is again another degree of freedom, okay, where we get another structural variant if we go to the hexagonal structure. And I maybe show here, you see, you can easily go also from the wood side structure to the structure which is related to graphene. So Andre's structure, Andre, I show it again. So, and you see, this is also the degree of freedom. Many of these wood side type structures, they simply change here the position of one atom, and then it goes from 3 neighbors. So here it's like sp3, it goes then to 2 neighbors. Okay, then it's more layered structure. Okay, so and this is what I talked a little bit about this now. Okay, yeah. This comes later. The structure of, so I simply want to give a little bit of taste so that you already have to remember that if you go from cubic to hexagonal, it becomes more complex and we have more degrees of freedom, you know? Because in the ideal case here, like this is the ideal case, the atoms are sitting exactly as near to as close to this blue atom as to this blue atom. But this is not always the case. So the tetrahedra can now become distorted, and very often is distorted in the hexagonal structure, okay? And this is one thing, we have more degrees of freedom because it's not always ideal close packed. And the other thing is that we have now, from the perspective, if we have the sodium chloride analog in the hexagonal close packed, we have 2 different surroundings. So one, if we look at from the perspective of nickel, it's surrounded by arsenic in an octahedral way, but the arsenic is surrounded by 6 nickels in a trigonal prismatic way. So we have different coordination polyeder because of the ABA stacking instead of the ABC stacking, okay, in the closed pack structure. So this is all the crystal structures, and I simply wanted to say, so from the 230 space groups, yes, some poor postdocs have to struggle with. Okay, yeah?
Just a very general question. So you're looking at the transfer calculations to find the materials which have charcoal insulated. But is there any anything you would really like to find, something with some property of some special type of transfer?
I always want to find what I said. I try to understand how we find the new materials, okay? So you predict new material, you predict a new concept, and we look for new materials. And one, what you should take back as a take-home message. So one thing is, if you find it in a binary compound, it's very easily to look in the related structure types for ternary and so on. You know, what I wanted to say, and very good for the question, is now what I showed you. If you start with mercury telluride, you already can invent many topological insulators. Now you are not surprised why suddenly many high impact papers come out with different compounds, which more or less always follow certain thinking paths, okay? So why don't we have so far good oxide materials? Because I think nobody has sit down. Oxide's even more, a little bit more complicated because they can be correlated and have charge carriers in oxides is more difficult. But it simply, it started with mercury telluride and bismuth. And so far, everybody thinks along the strings, okay? And this is what I wanted to explain. So we need heavy elements, and the heavy elements naturally have the s electrons inverted because they're contracted. So many of the semiconductors with heavy elements are automatically topological insulators. Okay? So, and how can we identify a semiconductor? I think Andre will come up with a very generalized paper in the language of physics. Okay? So you have to wait a little bit. I explain it now how we think and how we develop the strategy. Okay? And so the other thing is we have now already understood how we find this in this cubic structure, but we even allow this distortion because the distortion helps to open up a gap because we have this problem of that in the cubic always A, B, C or X, Y, Z is degenerated. So, and now I want to continue to simply say how you can do it then in the hexagonal and so on, and you will see we come even to the hourglass and understand why the hourglass or the properties. This is a little bit my strategy now, okay? So I really have a different approach than you, but we find the materials at the end, okay? So, but I simply want to give you as a real theoretician or whatever, or the DFT paper, so how the way is up. No, but simply also to find new materials, you know, you can identify later new materials, okay? So because it's not so difficult, because many of the materials are already there, and so the people who, like Bob, thinks like me, Kava, okay? So it's not surprising that, that we find the similar materials all the time. Okay, so as I said, in the cubic, everything is fixed, A, B, C, and alpha, beta, gamma is 90, it's the highest symmetry, but in the hexagonal, we already have that B is not equal C, but it's maybe its ratio is in the ideal case fixed, so which gives us a certain new degree of freedom. And I said, look, we can have the hexagonal diamond, we can have the wood side, the zinc blender, and now we can make the ternary analogon, which I already made, but it's like now, it always goes back to the end. We can even now understand, and this is what I want to show here, how the hexagonal diamond, the cubic diamond, and the graphite is related, okay? Because this is a ternary version of graphite. So, so this is therefore interesting. So here I simply want to say, if you compare the wood side structure, the gap of wood side, the gap of zinc blender, and the gap of the then corresponding graphite structure, the gap becomes smaller. So the largest gap is always in the cubic structure. So therefore, this growing in the hexagonal structure very often closes the gap. I skipped maybe this. Okay, yeah, now if we then go to some of the compounds, if you see here, scandium kappa tin and lanthanum kappa tin, they are both 18 valence electron compound. They can have even, very similar compound can have this wood side type, hexagonal diamond type structure, or they can have the graphite type structure. So which means the buckling of this layer becomes flat, and so these compounds are very often more metallic. And what you see in the band structure, or if you simply draw a molecular orbital, so you go from an sp3 hybridization to an sp2, which means here you have every atom has 4 neighbors because it's still in a tetrahedral surrounding, and here every neighbor has only 3 because it lost the contact to the upper neighbor because the structure is much more anisotropic. And if you see some of these topological Heuslers, they are crystallized in the, if they have small atoms, so they are crystallizing in the hexagonal structure, and then if the rare earth becomes larger, they're crystallizing in the cubic structure. So the relation between the, you can even predict partially whether there's a probability that the structure is the wood side version of a compound or the diamond version or zinc blender of a compound, because it has all to do with radio. I'll show one slide later. So here, instead of the sp3 hybrid, we have an sp2 hybrid structure, and this is like graphene. Okay? So in graphene, we have only one s electron and 2 p electrons hybridizing, and then one p orbital is left, and this is the one which is perpendicular to the layer, because there is where we remove the additional atom. And so therefore we get this additional electronic structure here like we have it in graphene. Okay, and so you can find the electronic structure, and this was one idea which we had. So you can find the electronic structure of graphene now also in this 8 or 18 valence electrons compound. And I said at the beginning, the problem with graphene was that the spin-orbit coupling was not large enough. So the reason why we looked then for this compounds was simply to find an electronic structure like graphene, and at the same time break the symmetry again to open up the gap, because we were also looking for topological insulators and not for a semi-metal like mercury telluride. So, and this is what we here did. So even then in the papers, we did some example like potassium mercury antimony, and now you know this is a compound of the hourglass of Andre, or some other composition with this compound. And I was simply aware about this compound. There are even not publication around about this compound made by German solid state chemists. I have all this PhD thesis. It's like a gold mine. Okay, so, but so therefore we thought, okay, these compounds are round and they have a nice band structure. So if you see the band structure of potassium mercury antimony, it exactly does. It does the band inversion, but it lifts the degeneration and it leads to gap. So I was very happy. Okay, as a chemist, I went to Benhai and said, look, I have the topological, not Heusler. Okay, we have to make compromises. It's hexagonal. Okay, so but he did some calculation and came back. So he said, okay, yeah, the s electrons, everything fits. It's really nicely inverting, you know. And the compounds exist in two different structures. One is like the honeycomb, is one with a smaller unit cell, one is with a bigger unit cell, because the mercury antimony is sometimes like that the mercury is sitting over an antimony. So you need two layers for and has a bigger unit cell. But it doesn't make a small difference in the properties, which is surprising. Okay, anyway. So as normal, he did very nice band structure calculation of V. I even can do the band structure by myself. We see the band inversion, and we see really the difference if we have here the potassium zinc phosphide or the mercury antimony. But here, this was the band structure, the surface structure. There was no surface state. So I was very, very unhappy. Anyway, I think we found a reason to publish also this in parallel. Okay, anyway. Good, but then there was hope, because then some theoretical physicists had this crazy idea of weak topological insulators, and Benhai came back and said, Claudia, we can save your paper. So we can make it a weak topological insulator, you know, because we have here the problem, since it's a layered structure, we get the band inversion at 2 points, at the gamma point and the A point. And if we have twice the inversion, it's again trivial. Okay, so our first idea. But this is a weak topological insulators. But this was not clear at the beginning. Okay, first then we thought maybe we find a compound where they have an inversion at one point, and at the other point it's not inverted. So we still keep the nice topological behavior. Okay, the good thing was when the theory predicted that there's something, so the Z2 is not only caring about the first number, they care a little bit also about the other number in the back. We were happy and we thought, okay, another nice paper to be right. So because, you know, twice, 2 times, then you simply defold your double Möbius stripe and you end up with a donut. Okay, so this was not so good. Okay, and our first suggestion was, okay, ignore, before the weak topological insulator was, okay, we should exactly find the case where one band is already inverting and the other not, which was a change because you really had to tune, but luckily this is again a class of materials where you have a large number of compounds so that you can find something where one point is inverted and the other not, so and then you suddenly get again your nice surface state, but unfortunately, so the energy gap is not what we wanted. We were looking for competition with bismuth selenide, okay, and not like a few milli-eV band gap. Anyway, and then because of the weak topological insulator, it was not so bad, so we could then make prediction for many compounds. Some are trivial, some are strong topological insulators, but only because they are not really insulators. They even have this crossing point, and some are weak topological insulators because they have double inversion, but still they are then. And then if you look at for weak topological insulators, so you don't look for the surface, you look then for the side states, and then you again get a nice surface state, okay, at the side, which is then difficult to cleave. But so since Ben Hai was still not happy with my compound, he even said, no, it's not worth to grow it, forget it. So we write these 2 nice papers, but growing the compound and sensitive to air, no, I think so to see something at the edge and only weak topological insulators, who cares? Okay, anyway, Andre cared, and now I'm allowed to grow this crystal, okay, finally. So we have the single crystal, so because it's more behind this simple compound, because they are these hourglasses. So he was happy that these compounds are existing, so it's not only wasting a time to go from cubic to hexagonal and so on, okay? So therefore, so if you think now back, even, and I think then we have a break, no? I don't know, I have not. So if we think simply back, it's already, with a few simple thinking and compounds, we already can do a lot in the field of topological insulators. And you now see we have already a big area of compounds with honeycombs and so on, which allows for prediction of interesting properties, you know, and I still think there's a lot to come. And so now we have to break from, I don't know, you know, half an hour break. Okay, thank you.